opening. Welcome, engineers and enthusiasts. In today's video, we're diving into the world of beam analysis using ANSYS. Beam analysis is a crucial component in structural engineering, allowing us to assess how beams behave under various loading conditions. It's used extensively in fields such as aerospace, automotive, civil engineering, and construction to design and optimize structural elements. We'll explore how ANSYS, a powerful simulation software, makes beam analysis easier and more accurate. By the end of this video, you'll have a solid understanding of both the basic and advanced techniques in beam analysis that can elevate your simulation skills to the next level. At its core, beam analysis involves understanding how beams deform under applied loads, and how internal forces such as bending moments, shear forces, and axial forces develop within the beam. Beam analysis helps engineers determine whether a beam will withstand the applied loads or fail due to factors like bending, buckling, or shear. Shear force distribution along the beam. While linear analysis works well for small deformations, real-world beams often undergo large deflections, plastic deformations, or nonlinear material behavior, making nonlinear analysis essential. Nonlinear analysis accounts for large deformations, material nonlinearity, and contact effects. Unlike linear analysis, which assumes proportional relationships between forces and deformations, nonlinear analysis takes into consideration the actual behavior of materials and structures beyond the elastic limit. To conduct a nonlinear beam analysis in ANSYS, you need to follow a few steps. First, define material nonlinearity by setting up the material model to handle nonlinear behavior, such as plasticity or viscoelasticity. Next, enable large deflection theory in the analysis settings to model the effects of significant beam bending. Finally, for beams interacting with other surfaces, include contact elements to simulate friction and separation. Here we'll take a beam subjected to a large point load and analyze the nonlinear deformation as it exceeds the elastic limit. Another advanced technique is buckling analysis, which is essential for beams under compressive loads. When a beam experiences compression, it can fail not by direct material failure but through buckling, where it deforms drastically out of shape. Buckling occurs when the compressive load exceeds a critical threshold, causing the beam to fail due to instability rather than material failure. So let's start by setting up the model. First, apply compressive loads to the beam and define the boundary conditions that mimic how the beam is supported in real life. Next, we run the eigenvalue buckling analysis. ANSYS will calculate the critical buckling load, which is the point at which the beam will buckle. Now let's interpret the results. The output will show the buckling mode shapes and the corresponding critical load for the beam. We'll demonstrate how to calculate the critical buckling load for a simply supported beam under compression and visualize the first buckling mode shape. Now let's look at a more complex real-world case study to demonstrate the application of beam analysis. Imagine we're analyzing a bridge beam subjected to a combination of uniform distributed loads and point loads at various locations. The beam is also fixed at one end and simply supported at the other. Step 1. Model the beam. Define the beam geometry with appropriate material properties, such as steel for high stiffness and durability. Step 2. Apply loads. Apply the uniform load representing the weight of the bridge deck, and point loads, representing vehicles. Step 3. Boundary conditions. Apply fixed and simply supported boundary conditions to the beam. Step 4. Run the analysis. Perform a linear beam analysis to determine the maximum deflection and the locations of maximum bending stress. Step 5. Post-processing. Use ANSYS's post-processing tools to visualize the results, including deflection and stress contours, and evaluate whether the beam meets the design criteria. This example illustrates how ANSYS can be used to simulate complex beam behaviors and optimize designs under multiple loading conditions. To summarize today's video, ANSYS provides powerful tools for both basic and advanced beam analysis, including non-linear analysis and buckling analysis, which are essential for realistic simulations. We covered how to model a simple beam, apply loads and boundary conditions, and interpret results. We also explored advanced techniques like non-linear analysis and buckling that give engineers the tools they need to simulate real-world behavior more accurately. Now, it's time to apply what you've learned. I encourage you to practice using ANSYS to model and analyze different beam structures, explore various load combinations, and refine your understanding of the software's powerful capabilities. If you have any questions or need clarification on any topic, feel free to leave a comment below. Don't forget to like, subscribe, and hit the notification bell for more advanced engineering tutorials. Until next time, happy analyzing.